Okay, let's get right into it. If you look at the trajectory of large language model architecture, especially over the last, say, 5 years, we've mostly been solving for sparsity in the parameter dimension.
Right, with things like mixture of experts, you decouple active parameters from the total number.
Exactly. But we still have this massive redundancy problem in what you could call the temporal dimension.
You're talking about the uniform compute paradigm.
I am. It's just standard transformer behavior. I mean,
Oh.
it doesn't matter if the model is processing a really complex token that needs deep reasoning or just a simple stop word.
The computational cost is identical.
Yes. We are spending the same number of FLOPs on the word the as we are on the word eigenvector.
Which is the fundamental inefficiency of the dense transformer stack. We're treating the token as the atomic unit of computation when it's really just the atomic unit of input.
And that distinction is exactly what we're unpacking today.
It is. We're looking at a paper titled ConceptMoE, Adaptive Token-to-Concept Compression for Implicit Compute Allocation. And this is from the research team at ByteDance Seed.
The core idea here is to shift all that heavy lifting from the token level to what they're calling the concept level.
Right, but it's different from earlier token merging papers, like Tome or some of the other heuristic approaches.
In what way?
Well, ConceptMoE claims to do this adaptively based on semantic density.
Yeah.
And maybe more importantly, it lays out this really rigorous framework for reinvesting the compute you save.
That reinvestment part is key, I think.
It's absolutely crucial. The authors aren't just trying to shave off some inference latency. They're actually trying to improve the entire performance to compute ratio.
So they set up this fair comparison methodology.
Yes, where they maintain the total FLOPs and parameters, but change the architecture to process fewer but much denser representations.
Okay, so let's map out that architecture first. It sounds like it's a kind of sandwich structure around a core MoE model.
That's a great way to put it. You have an encoder, then a chunk module, then the concept model, that's your MoE, then a dechunk module, and finally, the decoder.
The encoder and decoder are pretty standard, I assume.
Correct. Standard transformer layers. All the innovation is really in that compression pipeline in the middle, and it all starts with the chunk module.
And this isn't some fixed stride pooling layer.
Not at all. It's a learnable boundary detector.
Okay, let's drill down into that. The mechanics of the boundary detection. The paper mentions using query and key projections, WQ and white-K.
It's actually quite elegant. So for every token, let's call it A she sub n, they compute a query vector. Then they compare that query to the key vector of the previous token.
And the metric they use here is cosine similarity. Now, why that choice? I mean, I've seen other adaptive compute papers just use a simple linear layer, a binary classifier to predict split or merge.
Yeah, you could do that, but a linear router is just, it's super prone to overfitting.
It just memorizes patterns.
Exactly. It learns that united is usually followed by states, so it merges them. It's just looking at co-occurrences. But cosine similarity captures the intrinsic semantic orientation of the vectors.
So if the angle between the vectors is small, they're aligned. If it's large, it signals a shift.
Precisely. If that similarity drops, it indicates a semantic shift. They calculate a probability, P sub n, and if it's greater than 0.5, a new concept is initiated.
And the tokens inside that boundary are then aggregated.
Right, usually through a weighted average into a single concept representation.
But unconstrained compression seems risky. What stops the model from just collapsing everything into one concept, or the opposite, making every token its own concept?
That's where they bring in an auxiliary loss, LO. If you're familiar with the load balancing loss in a standard MoE router, it's conceptually very similar.
Ah, okay, so they're treating boundary and non-boundary decisions as if they were experts.
You got it. They set a target compression ratio, let's say R equals 2.
Meaning you want to average 2 tokens per concept?
Exactly. And the loss penalizes any deviation from that ratio across the whole batch.
Yeah.
This allows for sample-level variance, which is important. A complex sentence might only compress at 1.2, but a simple one might hit 3.0, as long as the batch average is on target.
Okay, so moving down the pipeline, we have our concepts. They pass through the concept model, the big MoE layers, but then we have to get back to token space for generation. That's the dechunk module.
Right, the inverse operation.
Yeah.
It maps concepts back to the token sequence length, but if you just copy and paste the concept vector, you create a big problem.
You get a step function, right, a really jagged representation.
And that would just wreak havoc on the gradients during backpropagation.
I can imagine.
It creates discontinuities that make decoding really unstable. So to solve this, they use an exponential moving average, or EMA, on the concept representations.
So it's like a low-pass filter on the semantic transition?
That's a perfect analogy. It smooths the trajectory, so even though the compute was discrete, the representational flow is continuous.
There's another detail on the decoder I wanted to highlight: joint decoding. The paper says the decoder attends to both the unpacked tokens and the concept representations.
Yeah, and this is a critical choice. The ablation studies back this up big time. Remember, the concept model is where all the FLOPs were spent. That's where the reasoning happened.
So if the decoder only looks at the unpacked vectors, it's getting a diluted signal.
It's losing all that rich information. By letting it also attend back to the original concept vectors, it maintains access to the dense, high-level features that the MoE layers generated.
And they showed that removing that joint attention caused a big performance drop.
A significant degradation. You just can't decouple the generation from its reasoning source.
Let's pivot to the methodology. This is where I think the paper really separates itself from a typical efficiency paper.
I agree. Usually you see a compressed model compared to a dense baseline, and they celebrate a speedup while kind of waving away a small drop in perplexity.
Or they compare it to a baseline with a different parameter count, which makes it impossible to isolate the actual architectural benefit.
But ConceptMoE sticks to this fair comparison constraint. Total parameters and total FLOPs are identical between the baseline and their model.
Okay, but if you're compressing the sequence length by half, you're inherently doing less compute. So you have saved FLO keys that you have to reinvest somewhere.
And they outline three main strategies for that. The first is just increasing the number of activated experts.
So instead of top 2, you can afford top 4, or even more.
Exactly. You're processing fewer items,
Yeah.
but you're processing each one more thoroughly.
Makes sense. What's the second strategy?
Layer looping.
Yeah.
This one is really interesting for anyone working on adapting existing models. You don't add any new weights. You iterate through the intermediate concept layers multiple times.
So you increase the effective depth without increasing the memory footprint.
You got it. And the third strategy is just increasing the hidden dimension size, making the model wider. This is mostly for pre-training from scratch.
So when they run this fair comparison, same FLOPs, same parameters, how do the results look?
They're consistently better. On language pre-training with open benchmarks, they report I think it was a
layperson might not sound like a lot.
no, but in a controlled pre-training setup on identical data, a nearly 1-point gain suggests a pretty fundamental improvement in data efficiency.
The more dramatic result was in long context modeling.
A plus 2.3-point improvement. And this makes intuitive sense, right? The whole lost in the middle problem in transformers is often about attention dispersion.
And by compressing the sequence, you're shortening the horizon.
Yes, a 4,000 token document becomes a 2,000 concept document. Relationships that were far apart are now effectively local.
I was also surprised they applied this to vision language tasks.
Me too. Usually vision token merging is handled by specific VIT techniques. But the principle holds. An image of a blue sky has immense redundancy.
You don't need 100 tokens for that.
Exactly. And I got a plus 0.6 improvement on VL benchmarks by compressing both the text and the image tokens.
Let's talk about the free lunch part of this. We've talked about matching the FLOPs, but some parts of the transformer, they scale with sequence length no matter what.
You're talking about attention complexity and the KD cache.
Right. Even if we match the dense compute, the attention mechanism scales quadratically.
And if you compress by a factor of R, that attention cost drops by a factor of R squared.
While the KV cache scales linearly.
Right, so this gives you a pure latency reduction you don't have to pay back. On NVIDIA Hopper GPUs, with a compression ratio of 2, they saw prefill speedups of 175%.
175%. And decoding.
Up to 117% on long sequences. The key insight here is that as your context grows, attention becomes the bottleneck. ConceptMoE just pushes that bottleneck further down the road.
So even when they doubled the layers with looping, it was still faster.
It was still faster than the baseline because the attention overhead was just so much lower.
I want to move to implementation, specifically continual training. For most of our listeners, pre-training a 90 billion parameter model from scratch is not exactly in the budget.
Yeah, not at all. But the paper claims this is backward compatible, and this is probably the most actionable finding. They took a pre-trained 90B MoE model,
A standard one.
a standard architecture,
Yeah.
and they just converted it to ConceptMoE. They didn't reinitialize anything. They used that layer looping strategy we talked about.
They called it ConceptMoE Top 11 Loop 8.
That's the one. They upped the activated experts to 11 and looped layers 8 times. The result was a plus 5 point gain on open benchmarks.
Wow. So you can retrofit an existing model and get a huge gain.
It shows you can, without the massive cost of pre-training from the ground up.
There was a nuance in the CT results about the compression ratio. They targeted R equals 1.5, but during pre-training, the model sort of drifted.
Yeah, it gravitated toward 1.81. And this just reflects the data. Pre-training data is noisy, it's high entropy. The model found it could compress it more aggressively.
But then during continual training on cleaner data,
It stabilized right at the target of 1.5. This suggests the adaptive part is really working. It's acting like a semantic entropy filter,
it compresses the fluff and expands on the dense parts.
creating a dynamic compute graph. That's the implicit compute allocation from the title. The model is self-regulating its compute spend based on how hard the sample is.
Let's get into the weeds of the ablation studies for a minute. We mentioned the cosine router, but they also talked about a stability issue where the boundary probabilities clustered around zero point 0.5.
Right, a common problem. If the model is always unsure, your compression becomes really unstable. A tiny floating point deviation could flip a boundary and change everything downstream.
So how do they fix that?
With noise injection, specifically Bernoulli noise. During training, they just randomly flip some of the boundary decisions.
You're forcing it to be more decisive.
Exactly. It's an entropy minimization tactic. It forces the probability distribution out toward the extremes, 0 or 1, and that makes the router much more robust.
They also tested the upper limits of compression. They pushed R all the way to 4.
And performance just collapsed, especially on reasoning and math tasks.
Why does math suffer more than prose?
Well, math has almost no redundancy. Every single token in an equation is critical. You can't just merge 2 plus and 2 and expect to keep the operational logic.
It suggests there's a kind of natural redundancy rate for language.
It seems to be somewhere between 1.5 and 2.0. Go beyond that, and you're performing lossy compression on information that really needs to be lossless.
Okay, so to summarize the whole contribution here, ConceptMoE gives us a way to decouple information flow from the raw token count.
Yes, it proves that by adaptively grouping tokens, you can apply deeper computation, more experts, more layers to the parts of the sequence that actually matter, and just skin the rest.
And it does all this while respecting the hardware realities of modern GPUs, but cutting down the memory down costs of attention and the KV cache.
It really transforms the sparsity discussion. We're not just talking about sparse weights anymore.
We're talking about sparse time.
It's a multidimensional sparsity. And the fact that you can achieve this through continual training on existing models makes it a really viable path for optimizing the models we already have, like Llama 3 or Mixtral.
You don't need a hyperscale pre-training cluster to benefit.
Not at all.
So a final thought for the researchers out there listening. If we're compressing tokens into these concept vectors, and those vectors are what's driving the reasoning in the MoE layers, we're essentially looking at a latent language of thought.
It's a huge interpretability question. I mean, if you were to analyze the properties of these concept embeddings, what would you find? Do they map to semantic clusters that are far more abstract than our vocabulary?
We might, in the long run, be able to bypass the tokenizer entirely.
That seems like the logical endpoint for this whole line of research.
We'll leave it there. For those who want to inspect the implementation, especially the gradient handling in that dechunk module, the ByteDance team has released the code in the paper's appendix.
It's a rigorous read, but yeah, highly recommended.
That's it for this deep dive. We'll see you on the next one.